Hello. Oh, can you hear
Good
me?
morning.
Good morning. Oh, got that. Thank you. Good morning. Good morning. And did you, excuse me, before I go any further, did you guys see that note in the waiting room? I never know if that works. Did you see that there was a,
Yes.
okay, great. Thank you. All right. Sorry about that, but I'm glad you, okay, so I'm here. So, all right. So, yes, I am. Now I'm going to get back into class here. Okay, so I'm looking at. So, hello, Mohammed. Hello, Angel. Hello, Jocelyn. Hello, Gabriella. Hello, Joshua. Hello, Lunar. Hello, Sydney, who I know. And many of you were here. By the way, I know many of you were here quite early, and I appreciate that too. And I was too until I got that call. All right. And hello, Nadine. Who else we got? Hello. Norma and Rebecca. Oh, what? Okay. Um, sorry. Apparently the phone is still okay. I'm confused. Okay. Good morning, Angelina. Good morning, Effie. Good morning, Norma. Good morning, Christopher. If I didn't say, good morning, Lunar for the double. Good morning, Genesis. Good morning, Gabriella, I think for the double. Good morning, Angel for the double. Good morning, Alexis. Morning, Gabby. Good morning, Nadine for the double. Good morning, Angel. Oh, and Angel, thank you for the answer. Got it. Okay. Good morning, Sinead. Someone's here. Good morning, Jibo. Good morning, Jean. Good morning, Rebecca. Good morning, Teresa. Good morning, Joshua for the double. There are many doubles. Sorry, I'm missing something. I'm a little. Good morning, Mohammed. Good morning, Sydney, who's here quite early. Totally noted. Good morning, Melanie. Good morning, Chanel. Good morning, George. Good morning, Jocelyn. All right, we definitely have a full house. Okay, we should do like physics. And if I didn't say your name, I apologize, but also maybe that means this is not a I hope it's clear. Like I'm saying hello to people I see, and then, or if I see an avatar, and then anybody in the chat. So it also might mean, so you might want to say good morning if I didn't acknowledge you at all. Um, okay. So you know what I want to do today? And I hope you saw, I think you did see that message. I'm not going to get all, I think you all saw that message also in the Google Classroom about that I realized over the weekend that Big Old Duck was also scheduled for today. That was just a complete mistake. That was from some landslide or cascade of, yeah, right, Angel. Thank you. Exactly. Right. So yes, so apparently you saw it. So just to confirm again, just the assignment dates have been readjusted to account for that or to. So what was due today was good. Thank you, Gabriella. I see that too. Okay. What was due today was the sheet called Midpoint Velocity, which, actually, in some ways, we're starting to get into the material now, but it's not a very long sheet, actually. I think I had misremembered it as very long. So what I'd love to do now is go over it more quickly than we often do. Or at least we'll give it a shot. We'll see. Because I have not forgotten about train of thought. You might have, some of you might have, or some of you might be wondering if we're ever going to. Train of thought is the next thing I want to talk about, even before we get to any new homeworks or anything. Let's at least, acknowledge your work here now that, and I want to establish one more equation. Warning, the thing that's written on the board right now. Okay, well, here's the summary of everything that's happening right now. The first, it says if A equals A naught. It says IFF A equals A naught. That notation might still be confusing some people. IFF means if and only if, okay, like for all time now. And A equals A naught, I mean, I think you're getting used to this. That means acceleration at any moment, instantaneous acceleration equals initial acceleration, right? A equals A naught means if the acceleration at any time is the same as the very starting acceleration. So that is a symbolic way of saying if acceleration is a constant. I'm reinforcing that now because I want you to get, for 2 semesters, I want you to get used to that notation. If anybody ever says blah equals blah naught, like X equals X sub zero, or V equals V sub zero, or any, that means that variable measurement is a constant. So where we're right now in the land, in the topic of constant acceleration, we're going to be we're going to be developing and analyzing a number of equations, concepts that are true only when, oh, interesting. Wait, I see the chat. I'm going to respond to that in a second, but very good. Okay, hold on. Oh, very deep question. Okay, yeah, I see you. Hold on. What I'm saying now, I'm going to write on the board. Hold on 1 second. What I'm saying now, the topic for right now, in a way, is constant acceleration. The conditions, circumstances, and equations that are true when acceleration is a constant. That's totally what was sort of introduced in the lab, whether we knew it or not. In lab two, then you took a sort of side road in lab three. I know we'll get to that soon. But then you're coming back in lab four. In lab four, absolutely, the background assumption is that acceleration of some kind in some axis is a constant. So there's a lot of things that follow when and only when acceleration is a constant. So we're going to be starting to develop some equations based on that. Now, the one that I wrote in blue on the board, warning, like reward for people paying attention, or pro tip for people paying attention. I would never memorize the thing that I wrote on the board here. That's like a step of explanation toward an equation that we're going to get to hopefully by the end of today that maybe you would memorize. But that's like a step that to catch your attention basically, and to explain something basically. So don't even bother trying to memorize that. But okay, so everything that's happening in homework 4 that we're about to go over, and certainly homework 5 that's next due, is all about constant acceleration. Now in the chat, okay, I'm seeing a couple of things in the chat. Good. Right. Okay. Wait. So there's one thing in the public chat, Angels, and then there's one thing in the private chat. I'm going to do this in order. I'm going to get to Angels second, just because something else came first in the direct chat. So somebody wrote, so this is like okay. And I definitely want both of you and anybody else, you should definitely submit in the points portals for points for these comments in the chat. Like, especially because one of them I'm about to respectfully and sort of gently disagree with part of it. But I don't want you to get the misunderstanding that means you said something wrong or you shouldn't have said it. Like, you direct chat person that I'm about to have a dialogue with, for it's totally relevant to everybody in this room. It's totally helpful. Yes, I'm going to correct something you said, but it was worth that you said. So here's what it is. Someone said, like in private, shouldn't my A have a bar on top? When there's a bar on top, the person saying, I thought that's what meant the variable was a constant. So that's a really interesting observation, because what you're absolutely right about is that often we do put bars on the top, and you're definitely right that this time I didn't. It's not right. Okay, now this sort of gets to what Angel's saying. Right, when we put a bar on top of a letter, we mean the average value of that letter, of that measurement. Okay, and here's the thing, why it's so deep that you said so. Angel's right. I mean we use bar not to mean constant, but to mean average. But here's why it's a deep remark that the person's making. I see what they're like, why the two can be easily confused or whatever. The point of an average is to give you one value that doesn't change, that represents a whole set of changing values. In other words, we all like to deal with constants more than we like to deal with change. I mean, constant is easier to deal with mathematically and scientifically. When a bunch of numbers change, in order to deal with them all at once, like with grades, right? I mean, the point is we want to put one grade on your transcript at the end of the semester that represents your work in general for the semester, right? But you do different works on different days. Right? So, like, right? Like you have an 80 on one exam, you have a 90 on another exam, you have a 100 on another exam. We want to be able to sum this whole situation up. And so what we do is we pick an average, right? We say your average for the semester was a 90. And what we're really doing when we say that, this is why this is a deep comment on the person's part. When we say your average in the class is when you got an 80 and a 90 and a 100, and we say your average is a 90, what we're not saying that you did get the same grade on every single test. But we're saying if we had to pick one grade that would be equivalent. Like if you had gotten the same grade on every test, what would it have been? Well, it wouldn't have been 100 because you only got that, like 100 would be too high. You often scored lower than 100. And 80 would be too low because you often scored higher than 80. But if we say 90, we're saying, you know what? She or he dipped below 90 just as much as they dipped above 90. So 90, if we're going to pretend that she got or he got the same grade on every single test, the one number we could pretend was a constant was 90. That's really what average means. Average is what you do when you don't have a constant, but you want to act as though you do, or you want to be able to have all the advantages of a constant. So long story short, so really it's a good question. When we've been saying bar up till now, that's because we didn't know how to deal with any individual numbers. We're taking one number that represents a whole, but it doesn't mean, but it means average, not constant. So now the way of saying, so now back to sort of Angel's like answer to the whole thing, like even if she was, is when I say A at any moment, like let me put it this way. If A equals A naught, if A at any moment is the same as the original A, well then it would follow then yes, it is true that the average is also the same as the original as because like if you got a 90 on every single test, oh, well then yeah, your average is a 90. So then you're at but that's what I but that so I mean I could say but I'm trying to say, what if every single value is the same as the original? That's what we call a constant. So hopefully, I don't know. I feel like that was a worthwhile question. Hopefully I answered. Maybe tell me in the private chat if I addressed that. I mean, I just went on for like 20 minutes, obviously, but I think, yeah, oh, great. All right, awesome. And thank you. Please give yourself tons of points. Now you get points also for the closing a conversational path. And thank you, Angel, because I think, yeah, and I think Angel addressed it. I'm basically agreeing with what she said. Constant acceleration. As long as as long, I would take out the word, just to be fair, to be honest, I would take out the word position from what Angel wrote in the chat. But other than that, I totally agree. So, okay. So we're doing constant acceleration now. So I think I'm going to just quickly, yeah, I'm going to go to the sheet. I'm going to screen share the sheet so we know what we're talking about. I'm going to like sort of bang out answers, I think, at first. I want to get to the second pro. All right. So bear with me. Let me. Okay. So this is what we're talking about, right? This sheet, I hope. And again, same thing as always. I know, I think most of you are really getting it. If you turned it in at all, like today when it was due, you got a bunch of points. You didn't get all the, you didn't get feedback because there's nothing for me to say about it yet. When you want, but I'm going to say stuff now so you'll know how to revise, blah, blah, blah. And then if you think you didn't need to revise, just re-upload the same. I think you get the system. But again, please understand, you got a bunch of points if you turned it in. And to get the remaining points, you listen now and do whatever revisions based on that. If you turned it in a couple of days ago or like last, you might have gotten even more points that like you sort of, you might even got more if you were that much earlier, but you're getting all of them once you incorporate these revisions, what I'm about to say right now, and or just re-upload it if you think it's perfect. Okay, so I'm going to actually, so this is the sheet we're talking about. Because I'm trying to make tracks here, I'm going to like just say stuff with the sheet up here, I think, until a certain point. And you stop me, please stop me in the chat if you have a difficulty with it. But in other words, I'm not writing out all the steps right now or anything. The particle starts out from rest. So yeah, but with an acceleration of 4 meters per second squared. We could write that as 4 meters per second squared. It's fine. You could write it either way. We're just trying to stress right now what that means. 4 meters per, it means 4 meters per second of velocity every second. And it says it accelerates at a constant rate. Okay. What you, well, the big lesson here, this is all like lab two. And like any lab, you didn't really necessarily know what you were doing when you were doing it. You were figuring things out. But in retrospect, the whole thing of lab two, I mean, the string lab is, that is what happens when objects do change their velocity. The object here is changing its velocity, but it's not changing its change, right? It's got a first derivative with respect to position. I mean, it's got a first derivative of position with respect to time, but its second derivative is zero. Like that's what we're looking at here. There's a change, but there's no change in the change. So like what does that, and that's a big thing in physics. So what does that mean? Okay, well, it means, okay, at the particle's instantaneous velocity, right at the beginning, it tells you it starts from rest. So the answer is zero for part A. Again, I'm just going to say the answers or a little bit of words. Stop me if you need more explanation or want more explanation or you disagree. So I think the answer to A is zero. I think the answer to B is 2 meters per second, right? Like it's gaining 4 every second, but it's constant. Like no matter what, it's gaining 4 meters per second every second. So therefore, in a half a second, it's going to gain 2. It's a constant pattern, if you like. So the answer for B is 2 meters per second. The answer for C is 4 meters per second. The answer for D is 6 meters per second. I mean, right? It's a pattern. You can imagine a table of values or a graph. We're just trying to show you what constant acceleration means. So the answer for E is 8 meters per second. The answer for F is 40 meters per second. You see where this is going? And you could imagine now, note, well, I'll do one more and then I'll say so. And then G is 80 meters per second. Now, in fact, I'm going to keep talking, but I want you to see something. Could you please put an electric hand up or say if you're with me so far, if like those answers are okay and like you got them too, or like okay, cool. Thank you, Bob, and thank you, Gabriella. Totally see it. All right, great. That's good enough for me. Okay, now note and thank you, Angel. Oh, I'm assuming that's a yeah. Okay, thank you, Angel. Awesome. And thank you, Lunar. I totally see that. Thank you, Joshua. I totally see that. Thank you. And there may be others. I can't see everybody on the screen because thank you, Sydney. Again, thank you for being so early. I'm gonna stop saying that, but I want you guys to know. I know. And again, rule of thumb for the whole class, I really notice the positive things. I want you to know that I see you when you do and when you do the negative things, I don't have time to look. Okay? Really, it's all about rewarding positives and being oblivious to negatives. And there's always chance to change. It's never too late. That's like a life point in this class. But okay. Now I want you to know something else. I'm saying the answers. You got the answers right. You're like, go on, Yaverbaum, go on. Yes. But notice where we're going. Look, is physics about equations? Yes, there's tons of equations. Like we're like seriously in equation land in physics. But one of the reasons we ramp up like this in physics 203 is I want you to see how much of this stuff you figure out sort of without equations, right? Now, yes, once we get the equations, maybe they make things faster and shorter, but the equations just capture a logic that already exists. The equations don't make anything true. The equations are just short, symbolic ways of expressing things that are already logically true, right? Like and there's something in the chat, sorry, but just to say that most of those numbers, the reason I can just say them in my head, and even though you have to show your work in your work, and I'm sorry, you do, but I know that a lot of those you could have done in your head. But realize that what you're doing is you're building an equation when you do that in your head. Like really, by the time I got to G, and I totally see the chat person, I will get the chat person, but by the time I got to G, what was I doing in my head? Just like you, I was multiplying 20 by 4. So there's some kind of equation in my head, like to get instantaneous velocity at a moment. Maybe I multiply acceleration by time, right? Like I don't have to memorize that. There's something about that that makes sense. And what it is me just rearranging the definition of average acceleration in my head. But okay, chat. Uh, oh, so funny. Oh my God. Okay, so the thing in the chat. Yeah. The thing in the chat, this is great, private chat, says, I'm a bit confused why you're just multiplying the values together. I thought it was much more complicated. I mean, thank you. That's exactly what I'm trying. I see you. Like, right, it seems like it'd be much more complicated. And look, of course it does get more complicated. But okay, I'm going to switch screens. I'm going to show you what I'm doing. And again, because this is the point, like we're here to learn, and the person who's asking that is just the one person who has the guts to ask. I guarantee. I mean, some of you already get it, fine, but you'll see something deeper in a minute, hopefully. But but I promise you that the person who's asking is not the only one who needs to see or wants to see like a little more explanation. So thank you. So here we go. Hold on. I just have to switch the screen. I get this wrong every time. Hold on. Stop the share. Okay. And this is sorry. This is homework 4, right? I think. Yeah. Correct me in the chat if but I think it's homework 4. Okay. Okay. I think A everybody knew because A was just a given. It just told you it was 0 at 0 seconds. But like, how did I get like that at T equals sorry. Okay, so I'm gonna skip to B, right? What B says. What is instantaneous velocity at sorry, at T equals 5? Okay, now look, again, many of you got this answer right, but nonetheless, that's all the more reason to pay attention. If you got the answer right and you think I'm about to say something you already know, I encourage you that this is all the more reason to pay attention because since you already got it right, your mind is relaxed. If you already got it right, your mind is relaxed. You're not worried, right? So you can just absorb what I'm about, and I'm serious about this. You can just now see if there's a possibility that I'm now going to say a different way of thinking about it that might help you more in the future. For example, I am going to show you now how this relates to equations, even if you didn't think you needed to do an equation to do this, okay? So, and again, with physics in general, some of you need me to say this right now because you are confused, legitimately and honestly. So maybe you're at the edge of your seat in that anxious way. Okay, so we could chill. I'm going to tell. But those of you don't ever think, oh, I already get this, so there's no point no, no, no. Whenever you think you get something, is all the more reason you could because you can listen in a different way. And I'm serious. It took me being in graduate school 2 times to really realize that. But the real lesson, I'm going to go back, I swear. But I promise you, none of this sinks in the first time, and it never sinks in the same way 2 times. I still find this stuff interesting because I get to think about it again and again and again and again. So don't think just because you've thought about it once, you're done and there's nothing value that can come out of it. Okay, and you get what I'm saying. Okay, so here's what I think about this. The equation I know, if you want to think in terms of equations, the equation I know is this. This is now what we're really focusing on for this homework and this topic. We're now focusing, and we haven't used it a lot. We're focusing on the definition of average acceleration is change in instantaneous velocity per time. Wait. Sorry. Oh, and I'm seeing things in the chat. Sorry. I see them, but I'm just going to do this and then I'll go back to, um, we are focusing on in that average acceleration is change in instantaneous velocity per time. I'm going to rearrange that now. But I want you, but look at it for a minute. It's really just an English definition written in symbols. It's just saying, what does acceleration mean? It means how you change your velocity in time, how you either speed up or slow down or change direction. That's all it's saying it means, right? But then that means I could rearrange it. I could say this, right? And now notice this is a double equal sign now. I just did algebra. This is not a definition of instantaneous velocity. The definition of instantaneous velocity is derivative of position, is dx dt. But this is saying if I ever want to know how fast something's going at a moment, well, I just ask, at what rate is it changing its fastness times how many moments did it travel, but also, in addition, how much did it start with? In other words, this thing that I just wrote is what I use. And well, I'll plug in the numbers here. I'll plug in and see. Sorry, wait. And here, now this is back to the other private chat person's discussion. By the way, this is great because different people are saying different things. I want you to know, so I really appreciate it. But when the other private chat person asked about A bar and all that, and Angel answered, like, here's where that part comes in. Like, A bar, you might think, do I know A bar? Like, was it ever given in this problem? I thought only A was given. But the point is that A was given to be the same all the time. Since A is the same all the time, then as a person in the private chat pointed out, then the average is whatever that A value. In other words, the average here is 4 because the acceleration is always 4. So I could say 4 meters per second times the time that we're looking at, which is for the first exercise, zero point 0.5 seconds, plus the initial velocity of 0 meters per second, right? So I get 2 meters per second is the answer for for B. Right now, that's how I got the answer. But everybody, bear with me for a second, especially the person who asked in the chat, like, wait, why are you just like multiplying? Notice what it now looks like when I'm done. I mean, now I've made it look more complicated, like you might have expected or wanted. But at the end of the day, I get the answer 2. What I'm saying at the end of the day for part B is every second I'm gaining 4. I started with 0. So after 1/2 a second, I didn't gain all of 4 yet. Like it takes me a full second to gain 4 units of speed. Only a 1/2 a second has gone by, so I've only gained half of that, which is 2. Like in the end of the day, I did just multiply 4 by zero point 0.5. Really, technically, what I did was I multiplied 4 by zero point 0.5 and I added 0 to that. Why'd I add 0? Because 0 is what I started with. So it looks at the end of the day, I just multiplied in my mind. Okay, so I will move on to say, but what I'm saying is number one, why I was able to just multiply and do nothing more complicated is partly the bonus fact, the very helpful, convenient, special fact that in this case, in this problem, I started with no velocity at all. If I had started with some velocity, yeah, then there'd be one more step in here. But the reason the multiplication is coming about at all is because I rearranged the definition of average acceleration, and that definition is division. I rearranged a division to make a multiplication. I'm going to say one more thing at the risk of like boring everybody, but also sidebar, I'm going to like defend myself too. I would say the reason we spent a long time on this, a fundamental principle of physics that carries through physics 204 and modern physics, 20th century physics, blah, 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 Einstein, is that there's a big relationship, but the big principle of physics is that acceleration and velocity are very similar and very related, but very different. Like getting down the difference between velocity and acceleration is like huge in physics. It's not a detail. It's fundamental, which means two things. It means one, it's okay if you're a little confused at first. You're not crazy or alone or stupid. Second of all, it's worth us all talking about for a while because it permeates everything in physics. Physics is a lot about the distinction or the relationship between velocity and acceleration. So, okay, so I'm like defending why I'm willing to like totally engage in this. So I'm going to say one more thing. Put it in examples. What are we saying in English? And I do want to show everybody that even the stuff that looks complicated in physics or looks like it should be complicated, it all is actually ways that you would think on your own if you had nothing else to do and you had enough time. None of this is actually like made up or like a weird way of thinking. It's just a very, very specific, focused way of thinking about stuff that you already really do believe, or at least that's my belief. For example, with this, just back off the whole thing, forget velocities, accelerations, and all that, and just say to yourself, if I had, in fact, I'm going to say this to everybody to bring us all back here. We will move on. I know it's 10 o'clock. Wait. Thank you, direct chat person, whose name might or may not begin with a letter that I might or might not mention. That's funny. I'm gonna do an exercise with everybody. Okay, like get whether you needed what I just said or not, or got anything out of it or not. To everybody, you're gonna put an answer in the direct chat. This is also an opportunity to get points, even if you get the wrong answer or like whatever. Imagine this, everybody. Okay, you have three eggs in your pocket. I mean, like eggs, what Easter eggs in your pocket. You have three Easter eggs in your pocket. And every day you gain two eggs. I don't know why. Like you're the Easter bunny. I don't know. Or like you're friends with the Easter bunny. Okay. You have three eggs in your pocket. Wow. Okay. Thank you. Every day you gain two eggs. I want in the direct. Okay. Oh, good. Right. Okay. But in the private chat, please. Oh, well, I'm not saying good. I mean, I'm saying good for the participation. I'm not saying whether she's right or wrong. But in the private chat, so it's not a race or anything like that. If you have three eggs in your pocket and every day you gain two eggs, then what I want to know is after 4 days, how many eggs are in your pocket? I'm going to say it again. You have three eggs in your pocket right now. Every day you gain two eggs. After 4 days, how much do you have in your pocket? I'm not, this is not a joke, nor am I like trying to insult anybody. Like it's to make sure we get, okay. And there is an answer. Like some people are, oh, this is great. By the way, I see the fire in the chat. This is awesome. Like you're all there. It makes me really happy. And some of you are putting really complicated things in the chat. If the complicated things are your work, that's great. But there is an answer, right? Like it lands on a, I'm looking for a number ultimately. And oh my God, I love this class. Holy crap, holy smokes. I think the whole chat is like on fire. I'm looking and I'm not, but I'm intentionally, it's not a race. So I'm not going to say like right or wrong until like pretty much everybody. And if you put anything in the chat, they totally submit for points. But right, it's pretty clear that you all, and if you don't understand the question, you didn't hear it, put that in the chat. But wow, it looks like people really are with me. Okay. Wow, wow, wow. Wow, wow. Yes, 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 yes. Oh my God. Okay, a couple of them are a little bit off, but okay, that was so really, guys, you really are a great class. And I hope you take Physics 204 next semester, and I hope you take it in person with me. We're working on the schedule right now. We're trying to work it out so that there's more in person. Well, maybe you don't like that. There's also going to be an online section, but we're trying to work it out so that there's more classes of 204 next semester that don't conflict with Orgo than ever before. So please stay with me. So this is great because I want to see you for real. Oh, thank you, Angel. Okay, good. I'm glad. Oh, good. I'm actually, I don't want to distract us, but I'm glad to hear that because I'm working on that right now. And if that is what you're saying, that good. Okay. All right. So look, no, and I'm saying that because this is amazing how much is in the direct chat. Like I'm not gonna like almost every one of you put something. And to cut to the chase, yes, I believe the answer is 11, which is what most of you put. I'm gonna say now some of you didn't, so I'm gonna say quickly. But thank you for like right. You've got three in your pocket right now. You're gaining two every day. So in 4 days, you'd gain two, and then four, then you'd gain four, then six, and then eight, right? You're gaining two every day. So two times four, right? Like 2 times 4 is 8 more eggs that you would gain, but you already had 3 in your pocket. So you'd have a total of 11 by the end, which is what most of you said. If those of you who didn't say it, don't feel criticized or shamed, but please let me know if you still don't get what I just said, or like later, let me know. I think you have 3. You're gaining 2 every day, but you do it for 4 days. So secretly, that's begging for multiplication. Like 4 days, 2 eggs each time. 2 eggs times 4 makes 8, but you already had 3. So it's a total of 11. Why am I dragging this out? Because I am saying that honestly, this thing right here, it is just saying that. It's saying, how fast am I going right now? Well, it's however fast, it's however much time I've been traveling for times how much speed I gained each one of those times, plus whatever I started with. Right? Now, the reason I'm dragging this out, I mean, yes, I do that. I'm dragging this out, but I'm pleading with you, and I think there's at least one person in the room who kind of just acknowledged it. I think there's at least one person in this room who actually did get the answer, who knew the answer, and didn't use an equation. But now what I'm trying to show you is, so you just made up an equation in your head, right? What I'm trying to show everybody, yes, I'm trying to show that the equations make sense. And yeah, I'm those of you who can't just do this in your head, which is also me, by the way. I'm not that smart. Like I'm trying to show you if you want to think in terms of equation, yeah, there's an equation for this that you already had that you could rewrite. But I'm also trying to show all of you, like equations are just statements of things that we do. They make sense. Those many of you did that equation without even thinking of it as an equation, which means you invented an equation. You're not just memorizing and plugging in. You are discovering the equation the same way that, Newton or Galileo or whatever. And that's really important to think of physics that way. This is all within our grasp. It's not magic. It's miraculous, but it's not magic. Okay, so hopefully, yes, thank you. I see that in the chat. Yes, yes. So I'm going to get back to the work, obviously, to the homework. What I'm hoping now, so that's why it just seemed like I was multiplying. The reason it just seemed like I was just multiplying is because I was, but I was also technically I was multiplying and adding 0 every time. If this whole problem, the thing had started with a different velocity other than 0, it'd be the same process, but yeah, the numbers would be different. Okay. Oh, no, thank you. Thank you for the direct chat person about the third eye. Awesome. And okay, no, great. And I am, well, okay, but really, I'm also particularly hoping that the person that originally asked this in direct chat, let me just see if that person is still with, hold on. It was that person. Oh my God, the person that just said third eye. So thank you. So that worked for you. Oh, great. Okay, then I'm going to retire right now. I'm going to, good, good. All right, so I'm going to move on though then. Um, okay, so those are the answers. So I think we got the answers for those then that way. And summary, the equation that we're working with right now, you know, is the thing to memorize is this. And then you can rearrange it to make you see the difference between triple equal sign and double equal sign, right? Because I also could have rearranged it a different way to solve for time or whatever. Okay. Okay. I'm going back to the sheet. Hold on. Okay. Then it says draw a neat, careful scale graph. Well, okay, I can do that. We can do that. And here's what it means to now look. I don't want to make any assumptions, but if you're anything like I was for decades, perhaps maybe you hate graphs. If you hate graphs, you're not alone. I get it. Do I hate graphs now? No, I love graphs now. But it took me decades to like graphs. And one of the reasons it took, and I hated them when I had like, but one of the reasons I used to hate them is I misunderstood that, like kind of like the discussion we just had, the point of graphs is not to make life more complicated. Yeah, it seems that way, but the point of graphs is to make life more simple. The point of graphs is to take a whole bunch of information of variation and details that change and distill them down to a simple, clear picture, a trend. So when we say a graph in physics, we're looking for 3 things. 3 key elements. a simple trend, shape. Like sometimes it's called a trend line, right? But it's not always a line. It could be a curve. But what the point of a graph is to show a relationship. And the way you show a relationship is you show it with a simple picture, a simple trend. But the simple trend doesn't tell you the relationship unless you have two axes that are labeled, right? The trend is always showing a relationship between one variable and another. So the axes, it must be clear what those variables are. Otherwise, the shape is not saying anything. And then the other thing that a graph generally should have, and I'm talking physics here, not in math. When in math, maybe you're like learning how to make the graphs, but in physics, they're supposed to be the results of experiments and data and blah. Um, so you take all this data in the lab and use Logger Pro and all of that to ultimately get tables of values, to ultimately get a scatter plot, to ultimately turn into a simple shape on two axes that also has. What we call a graph in physics is the finished product, which means a shape on two labeled axes with like a point or two labeled so that you have a sense of scale of the whole thing. And usually that key point will be like a y-intercept. And once you have that, and maybe an x value as well, just so that you see like what kind of quantities we're dealing with. Like, are they centimeters, or are they like miles, whatever. So the graph for this, so I don't, did you catch? So the three things we need: a trend, labeled axes, and a couple of key points. So the graph for this, what we're looking for is to see this pattern. Sorry. This is the graph. I think. Wait. Yeah. And then it's going to ask you about the well, yeah. I mean, that's the graph. Or you could even do like this if you want. But you see, like the point is that this. Oh, sorry. Except it's so I did it so carelessly. I meant to go straight through the origin. I mean, that is correct, but it was too sloppy. Hold on. Did it again. Okay, that's the graph. And notice the key thing that's happening here is we're putting velocity on the dependent axis, time on the independent axis, and what we're getting across is velocity does change in time, but it changes at a constant rate, i.e., this graph is a straight line. I'm not saying all velocity graphs are straight lines, but a velocity graph, but it's not a horizontal line. We're not saying that the velocity is always the same. We're saying it's different every second, but it's different by the same amount. The slope, the rise over the run, is a constant. Like, in other words, delta V over delta T is one number, which is 4 meters per second over seconds. You see how it relates? The slope is constant. The slope is 4. The y-intercept is 0. That's all the information that was captured in a graph. That's what we're saying. And that's what would express an object in free fall is, I mean, well, I guess that's a whole, but that's the point of lab two, is that change in velocity without a change in the change is what apparently naturally happens near the surface of the Earth. Like that's the physics tie-in. The second derivative exi the first derivative exists, the second derivative is zero when things freely fall to Earth. That's like the physics math point here, but it's just something in the there's a bunch of wait, so right. Oh, okay. So I think someone answered their own question in the direct chat. Yeah, I'm saying it's linear. This is linear. If, and before I get to the next direct chat, if, but this is where the labeled axis, okay, just to be clear, if, well, I guess this is where the problem then goes. And if we don't get to the train today, we don't get to, well, I'd like to start it, but if I had done position versus time, which is not what the question asked, but certainly could be a good question. If I had asked what's happening with meters per second, then that would look more like this. That would be a quadratic or a curve. Do you see? I'll just leave it at that for the minute, but the, right, it matters what we're graphing. But okay, let me just look at there's something in the chat. Just like the intervals in your axis per dash is fine, okay, for scale. Or like, yeah, wait. Oh, wait. Okay, there's two questions from the same person in the chat. These are all great questions. The intervals of my axes per dash is fine. Yeah, yeah, it's you can do it. I mean, usually if there's a y-intercept that's other than zero, I would sort of make that explicit. I mean, here the y-intercept was zero, so I just sort of did it the way I did. But yes, you don't need any. What I'm really saying to everybody, or and the person in direct chat is like, yeah, whenever we ask for a graph from here on, I mean, especially if it's not in lab, if we ask for a graph, we just want like a simple picture like that. In lab, you have to go through much more work to get it because in lab, you're collecting the data to create the graph. But your final graph, even in a lab, shouldn't be a whole bunch of dots. It should be the trend line that got extrapolated from the dots, if that makes it. But so yes, to answer your direct, it's that you just label the way I did. Now, oh, yeah, right, you didn't have to, right. You didn't have to notate the y-intercept point explicitly. I mean, here it's because it was zero. It often would help to if it's not zero. But yeah, now the free fall formula is where I'm heading with all the because the person also asked, great question. Someone asked in direct chat, like, what's the free fall like formula or what I would call equation? The only reason I'm not going to answer that just yet, that's where I'm trying to head with this whole thing. That's sort of the goal by the end of the sheet. So bear with me. But yeah, that's where this is heading. Okay, okay. And maybe I'm just about there, actually. Let me just look back at the sheet now. So that's a graph. Um, Okay, but again, so because I see where these next questions are going, what's very frustrating to a lot of people at the beginning of physics, or at least the way we teach it here, like I know that many of you were expecting like that physics is like we give you formulas and equations and then you learn to plug in them. And right, what I'm saying is in a way, physics is a lot easier than a lot of you think. But in a way, at first, it's harder because what we're really saying is no, physics isn't about using equations. Physics is about developing equations. But that's what we're trying to show you how to do now. So again, I guess this is also my way of saying those of you who feel like we're not doing physics until we have a whole bunch of equations, that's not really true. Like we really are doing physics. Um, and in a way, it's easier than you might think, but in a way, it's harder. But it's only harder because it's a surprise. It's actually not harder. It just feels harder because you might have been gearing up for something else, for whatever. So example of that. Why I'm saying that? Wait, someone's in the waiting room. Sorry. Okay, example of that. I'm looking at the sheet. Is the next question? What's the average velocity during the first 2 seconds of its trip? Okay. What's the average velocity during the first 2 seconds of its trip? So this is worth like actually talking about. Um, well, I mean, I think the answer is four. Just okay. I think the answer is four. But well, I'll say I think the answer is four for question I. But I'm going to explain that in a minute, obviously. But okay, just to be clear, answer is 4 meters per second. And I think that the answer for J, just to be clear, um, is uh, is 4D, right? Yeah. Yeah. But now, like, where'd I get that? We we I'll go to equations here because now we're trying to practice like this other equation that we just got recently. That again, I think makes sense, but it takes getting used to. Average velocity. So I'm doing these both together, same way. The question, the question is, what's the average velocity for some time interval, right? Now, if you're doing the five-step method and so forth, step three, like we know, like I've been failing to draw diagrams here. You do have to draw diagrams in your homework. I'm just trying to like stay on task, so I haven't been drawing diagrams. But obviously, we know what the question. So that's step one. Step two, I wrote down the question. Step three, you would write down some general principle or definition about average velocity that's like that's true in general, but that might be relevant here. So let me be very clear to all of you. One of the first thing we learned in the whole year, if we're doing like a step three, the first thing we learned in the whole year was this. This is a definition of average velocity. Right? This is a definition of average velocity. It is definition. It is always true. If you were doing your homework right now or taking an exam and you wrote that down for step three, you would get points for it. It is a correct and good thing to do on every level. And it helps your thinking move along. Here's how it helps and it really helps your thinking move along by writing it down. Because what many of you might realize somewhere in your mind is now that I've written this down, you might say, okay, but wait, I didn't use that. Or you might be saying, wait, but I can't use it. Wait, this is actually what bothers me about this problem. Like, I remember that we learned that, but like, that's totally not helpful here because you might say, I don't know anything about the X's. And you're correct, right? Or let me put it another way. If you do start plugging and chugging into this right now, if you go straight to step four and start plugging and chugging into this, something is going to go wrong because you don't have values to plug in for X. Or you might go start trying to solve for them, which is really what happens in the rest of the homework. But you don't need to. What I'm saying here is if you it or really, I'm talking to, or some of you might not have even gotten this far because something in your brain might have jammed up. It certainly would have for me. Something in my brain jams up about this question, I and J. I'm like, wait, it seems fair. It seems reasonable, but like, what? Wait, do I have an equation for this? Do I know how to do this? The average velocity for the whole 20-second trip? Like, what is that all about? And here's where the five-step method really helps is because if you look at the question, it does seem hard for some of us. I mean, maybe some of us it's not. For me, it would have been hard. If I look at that question, I'm like, wait, the average velocity for the 20-second trip, like, I don't, wait, what? I mean, average velocity, like, usually I used to do like displacement divided by time, but like something seems wrong. Do I have the displacement? Like, no, that's not what he's saying. So what? And if you don't write anything down, my brain just like crumples on itself and I get pissed off at myself or at the professor. Like, honestly. But if I follow the five-step method and I write down what I do know about average velocity, then I will look at it and realize, that's why I don't like this question because like that is a true statement. And Yaverbaum's going to give me points for that because it is going to help me. But in fact, it helps me by me looking at it and saying, I don't know what the X's are. So maybe that is not the only statement I should be thinking about right now. Maybe there is something else I'm not thinking. And there is. It's the other thing we just learned at the end of the last sheet. What I can say, and it even says, hint, notice there's a steady change in velocity per time. Like what it's saying is, like, hint, sorry, acceleration is a constant, right? And what we learned at what we started to learn at the end of the last class is that when acceleration is a constant, certain truths lock into place. What we learned last time is that if and only if acceleration is a constant, then mean velocity is the same thing as median velocity. That was the point of that seemingly weird last problem with the numbers, the rows of numbers that you were averaging, in homework three. That when the numbers are increasing or decreasing by a steady rate, then the mean equals the median. What does that mean in physics terms or in equation terms? That means that the average velocity is the middle velocity. The average velocity for the whole thing is the average of just the lowest and the highest, just the lowest added to the highest divided by 2. You right? This is the takeaway. And this is a very important and non-obvious takeaway from the last sheet. Sorry, I'm all over the place with the sheet. Okay, wait. Oh, right. Well, I'm explaining. Right. Okay, sorry. I'm seeing in the direct chat. Yeah, 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 yeah. Right. Right. Well, that's what I'm explaining. Okay, wait, I'm seeing the draft. How did I get 40 for J? Here's how. I use this equation. This equation is a different equation for average velocity. It's not the definition. It's not always true. It's not the first thing I should write down. The other one is always the first thing I should write down because it's always true. But this one is true when and only when acceleration is a constant, which is true here in this case. Acceleration is a constant. Then average velocity is the middle velocity. It is just the average of the lowest and the highest. So here I'm saying, so for question J, if that's what you're asking. For question J, average velocity is the average of the lowest with the highest, i.e., 0 meters per second plus 80 meters, was it? Yeah, 80 meters per second divided by 2, which is 40 meters per second. And if you're wondering, well, wait a minute, where did I get the 80 from? Well, 80 was the answer to question G. So what we're literally saying, I'm watching the time, I promise. What we're literally saying here, well, is we are I'm kind of saying these things are starting to get a little deep now. On the one hand, a big lesson of the class is there's average for the whole is not the same idea as any individual value, right? Like V bar, and that's why again I'm so excited that somebody in the direct chat, like right away at the beginning of class, was like, "Wait, what about why are there no bars? Or like, what's the deal with that? Or having a bar or not over a letter?" And I'm saying, right, hey, big difference. When there's a bar, it's the average value of a bunch of values. When there's no bar, it's any individual value. But the way to sort of go back and forth between the two ideas is if you have the luxury of knowing that the values are changing in a constant way, if velocity is changing, if there is acceleration, but the acceleration is not accelerating, if the acceleration is a constant, then the individual velocity right at the middle, the instantaneous velocity, v without a bar, right at the middle, right at halfway through the time, is literally exactly the average for the whole thing. As long as the pattern is steady, like that's what we were saying with those numbers last time. As long as so acceleration being constant means like the pattern is steady. We can rely on it. We can make some really straightforward predictions, such as what's going to happen right in the middle is the average. So the average here for the whole deal is 40. That's what I'm saying. Hopefully I'm gonna look back and I'm going back and forth between screens. Wait. Yeah. Wait. So really I'm looking at the so by the way, direct chat person who asked, how did I get 40 for J? I know I talked a lot just now, but please tell me if I did answer the question, sort of. But then there's another person in the direct chat who's sort of answering questions. Oh, thank you. Okay, great. Awesome. Thank you. It's Yes, okay, I'm going to say this quickly. There's a person in direct chat, and I appreciate totally like the feedback and the dialogue that's happening in the direct chat. What I think, how can I put this? What's good that I'm going to extract, what's good is somebody in the direct chat is like making analogies. Should I read it? Well, it's making analogies, and analogies are a great way to understand this physics. Like, what is an analogy that really works is, I'll say quickly, there is definitely an analogy between acceleration and velocity. Average velocity is change in instantaneous position per time. Average acceleration is change in instantaneous velocity per time. You should think of them as like parallel buckets or whatever. And it's not a coincidence because velocity is the derivative of so now instantaneous, like a different analogy, but all is that instantaneous velocity is the derivative of position with respect to time. Instantaneous acceleration is the derivative of velocity with respect to time. It's definitely an analogy. Now, but someone in the chat is also seeing that there's something sort of analogous between two other equations, but I want to caution everybody that it's less perfectly analogous than this. The other thing that someone's seeing in the chat is like there's this. Oops, sorry. Like these two, yeah, I see what you're right. I just want to like so someone I believe is saying that these two are sort of like similar, and you could sort of make an analogy from one to the other. I I like the observation and I like the whole way of like thinking by analogy, but I just want to caution everybody, if you write these two down, they're similar, but they're not the same. Notice that one is a minus sign and the other is a plus. And to be really frank, one reason I caution against just trying to like blindly memorize equations. If you try to memorize things, these get very easily confused. If you just memorize them without trying to really understand them, they're easily like people never remember. Should I put the two here or the t there, or is this one minus or is that one plus? But if you stand back and look at what they mean, the top one is saying difference in position per time. It's subtraction because it's like, how far did you get per time? I mean, literally, it's saying, how far did you get displaced? But the bottom one is addition. It's addition and it's divided by two because the bottom one, we're really saying, sorry, just to have these all written down now, just so you can see. Oh, no, I guess it is. Sorry, I did write it down. Sorry. The bottom one, we're literally averaging. We're literally averaging. We're saying take the first velocity, add it to the second one. That's two velocities that you just add together. So divide by two. You're literally taking the average. I like, and notice, uh, they're both equations for average velocity. They're really easy to get confused. This is again why I stress the five-step method and doing things like if you were ever in an exam and you didn't know which one to use, and you knew you were being asked something about average velocity, but you didn't know, should I use that average velocity statement or the bottom average velocity statement? What I'm trying to get you to see is notice the top one is a triple equal sign. The bottom one isn't. The top one is a definition. It's always true. So it's always correct to write down. You write it down, you get points. You're not wrong. It's right. Then you look at it and you're like, can I use it? Is it useful? Is it going to do what I need? And if you say to yourself, no, it's not doing what I need, Then you write down the next one. But this is why it's worth writing these things down. Sidebar, sorry, I know today's turning into like, well, I guess every day is like preaching the sermon that I need to hear. But like one of the reasons we write down all of our steps, it's not to prove to the teacher that we know the steps. That's not the point. The point is that by writing down the steps, you're actually taking steps that you don't take unless you write, and you don't get to the end of the journey unless you write. What I mean by that is a lot of the reason that a lot of people don't like writing things down, I mean, definitely including me, is that secretly inside my heart, I want to do well. I want to be right and I want to be approved, by whomever, so professor, whatever. So in my heart, I don't like writing things down unless I'm super confident that they're correct. I don't like writing things until I know they're right. But the secret to science, the secret to academic success is flip that script. Don't wait till something's correct to write it down. Write crap down until it becomes correct because you can't see it the same way in your mind as you can on paper. By writing it down, you're working it out. You're seeing what's missing and what, I mean, you know this in fourth grade, right? But it becomes very easy to forget when you want to be perfect. So this is why I'm giving you all these points for drafts and redrafts and revisions, because the point of writing things down is not to commit to a Nobel Prize or you're not marrying the piece of paper. You know what I'm saying? Like your work. So these two equations, the first one is what you should always write down first. But then notice the second one is what will sometimes be true, sometimes be true. The average velocity will just be the average of the velocities, but only if and only if the acceleration is a constant. So that's why we have to actually learn about the rate of change of velocity in order to really understand velocity. Okay, that's like the big lesson here. Okay. Okay. So I'm looking. Okay. I'm looking at the chat. Position versus velocity. Yes. Good. Very good. But the person in the chat who says position versus velocity as well, units as well. Yes. Right. And then shouldn't it be equal? Wait. Shouldn't it be as it's? I'm saying. Wait. I'm not sure. I'm not sure if I'm agreeing or. Oh. Yeah, probably. Yes, I think we're discussing. Yes, sorry, we're not going to get to the train of thought now because I hope this is useful for people, and I apologize, but I promise we're not. The next thing we're doing is train of thought. Yes, I think it's tabled for now, for good or for bad, but because we're going to wrap this up, we're at least going to finish this sheet. It goes to 10. Oh, sorry, I've been thinking it goes to 10:50. It goes to 10:40. Right, but we still have 3 minutes. But yes, we only have 3 minutes. I thought we had 13. We only have three. That's correct. Thank you. But on this thing, I will stand by this. I am saying the top one is triple. The bottom one is not a triple. It's equal sign. It's only true if the acceleration is a constant. And by the way, it circles all the way back to homework two. Like homework two, I mean, this is where physics is not as complicated as you think. It's simpler than you might think, but that doesn't mean it's easy. Like there's fewer ideas to manage than you might think, and there's actually fewer equations to manage than you might think, but you got to really manage them. The goal of physics is to get as much information as possible out of as few ideas. So therefore what I'm saying, okay, fair enough, thank you, direct type person, got you. Okay, I'm going to wrap up in a second. But if you're trying to like follow this course, the homework number two with Hill figure, like those of us who thought, oh, okay, going up 40, coming down 60, I'll just average the two together and I'll get 50. What I'm telling you, what I told you then was you can't do that. What I'm telling you now is, well, you could sometimes do that. You could sometimes do that. You could sometimes say that the average velocity is the average velocity. Sorry. You could sometimes say that the average velocity is the average of velocities, but only sometimes. What sometimes? When the velocities are changing in a steady, constant way, which was not happening in the Hill figure problem. First, you were going at 40 miles per hour, which means you had an acceleration of zero, like you were constantly going 40, always 40. So you had acceleration of zero. Then you changed your velocity to 60. So now you have an acceleration of something. You changed it from 40 to 60, maybe very quickly. So you have an acceleration of something, and then you were going 60 constantly all the way down the hill. So you had acceleration of zero again. So your acceleration spiked. So that's why you can't just like, so this equation did not apply to homework two. We didn't know it then, we didn't use it then. And it would have, and anybody who did use it was premature and it was wrong. Right? But now we're saying as long as acceleration is steady, oh, then you can average velocities to get average velocity. Okay, okay. So acceleration matters. Okay. I guess that's a good. We didn't finish. No. Well. Oh. Okay. Well, that's a good stopping point. We don't have class Wednesday, correct? I mean, I should be. I shouldn't be the one asking this, but
Correct.
correct. Right. Okay. Thank you. Yes. So, and not the rest of this week. There's no like makeup day this week. Correct. Sorry. Like we're done for the. I think. Right. Does anybody? Well, anyway, you guys can go. But if right. This is it till next. Okay. Thank you, Christopher. Okay. So anyway, so thank you for your indulgence with all this. I hope that was helpful in some way. We'll just keep going. I'll look at the assignment dates to make sure they're still all appropriate. And I'm hanging out if there's any questions. But thank you all very much and have a great day. Thank you.
Thank you.
Thank you. Thank you.
Thank you. Have a good day.